how to talk to satellites. So I want you to think for a minute, how many people remember the movie E.T.? All right, maybe you recognize that picture then. Oh, good. I asked this of my students. I had my students come to my office and I say, hey, does anybody recognize that picture? And they all said no. And I was really sorely disappointed by that. But this is, in fact, the communication device that E.T. built to call home. And you can see it has some really useful things in terms of what we're going to talk about today. Specifically, it has an encoder device. That's the little speak and spell. It then takes that encoded message and makes it an electrical signal. Those are those hair clips on the hanger. The hair clips on the hanger then are connected to this record player that will then modulate that signal onto a carrier, which is then sent out that umbrella antenna that you see in the back. Okay? So that's what we're going to talk about today. We're going to talk about each of those pieces and why we might want them and why they're needed in satellite communication. And I should warn you that what I'm really going to try to do today is condense a semester-long graduate class into the next half hour. So I hope you're taking notes. There will be a quiz at the end. All right, before we start, I really do want to introduce you to my lab, Space Systems Engineering program. Bob mentioned that. This is an Alaska Space Grant sponsored program, and the purpose of the program is really to collect some transdisciplinary students into multidisciplinary teams, and we design NASA-relevant hardware. So it has a design, build, fly paradigm, and we have done that with rocket payloads that we have launched out at Poker Flat, and we have done that with satellites, and I want to point out that those pictures are of a satellite that we've already launched. This happens to be the engineering model of that satellite, and you're welcome later to come up and touch it and feel it. This is the satellite. It is exactly this size. This is called a CubeSat, okay? And this satellite was designed and built by students up at UAF. All right, so that's what we do. So these are my students. They've all graduated. They're all working for places like Boeing and Lockheed Martin and places like that. Alaska Satellite Facility, out at the NOAA facility outside of Fox. All my students work on there. Now, I'm a classically trained engineer. And what that means is that I solve technical problems so that people can reach their goals or manage the mission that they're attempting to do, all right? So in order to do that, we have to identify a need, right? And we have to identify what are those problems that keep us from being able to achieve that need. And then we find what are the solutions to those problems. Okay, so that's the process that an engineer goes through. I have a need. There's some goal that I'm looking for. Identify the problems, find the solutions to those problems, then you have met the need, right? So that's what we do. And that's what we're going to talk about today. So what is the need? Well, the need is that I have a daughter who goes to school in Virginia. Here I am up here in Alaska. There's my daughter down there in Virginia, right? I'm a recently empty nester, so she's still in college, and I have a need to communicate with her, okay? And the difficulty is that Virginia is a whole long way away from Alaska. And in fact, it is not in line of sight, right? Like Virginia is like there somewhere, right? So I have a problem, right? I have a need. I want to talk with my daughter. I have a problem in that she's really far away and not line of sight. Well, I can solve one of those by talking through a satellite, hence the need to talk through a satellite. That gets rid of the line of sight problem. I still have a distance problem. But I have more of a problem because I'm not the only one with daughters who you want to talk to. And in fact, there's millions of people who want to be talking, and they all want to be talking through my satellite, right? And that's a problem for me, because I want to be heard. And if you can imagine this room, if everybody was carrying on a conversation all at the same time in this same space, nobody would be able to hear anything, right? So that's a problem for me. The other problem is we're all talking different languages. Well, maybe not in this room, but across the millions of people who want to actually talk through this satellite, we're all talking different languages. And that also is a problem, right? So these are a lot of the problems that I have to manage if I want to talk to my satellite and let my daughter hear it. Okay, so let's go through this and figure out how do we manage this. All right, so standard satellite system, all right, has a transmitter on the ground, has a satellite up in the air, has a receiver on the ground. All the smarts are on the ground. All the satellite is doing in this communication system is it is receiving a weak signal, re-amplifying it, and translating that signal to a different frequency so that the uplink and downlink don't interfere with each other, and then sending the signal back down again. That's all it's doing. So they do that through a box called a transponder, okay? This satellite, for most communication systems, is sitting up in geosynchronous orbit. That's about 36,000 kilometers above the Earth. Okay, so geosynchronous orbit says that the satellite always looks in the same place in the sky all the time. Okay, so I don't have to move my antenna around, right? I'm always looking at one place, right? There's probably over 2,000 communication satellites in orbit around the Earth right now. This includes military as well as civilian satellites, okay? And I want to talk to them. The things that I want to say are in a different language. We have voice, I text, I send her pictures of the cat, right? And all of these things are different. When I talk to you, you have an ear and you can understand what I'm saying. And when I text, you hear that through your eyes, right? But to the satellite, it only has one side of sensors. It doesn't have ears and eyes, it only has one thing. And in fact, it only talks one language, and that's binary. It talks 101101101110, right? That's all it talks. It doesn't know how to talk voice, it doesn't know how to talk text, and it doesn't know how to talk pictures. So we have to figure out how to translate our language into something that the computer understands so that it can hear it and send it back down, all right? So that's sort of step one, is to deal with the language issue, all right? So how do I deal with the language issue? Here we go, text. That's the easiest thing to do, and you all probably know all about it and use it every day. Anybody who uses a computer uses this code, okay? Now, the reality is, I don't care what the code is. You know, you get your Cracker Box decoder ring, you know, and as long as it's just you and your buddy, you can make up any code you want, but you have to agree to it. Because if you're using one code and you're using a different code, then you won't understand each other, all right? So we have standards. Now, the computer keyboard has a standard called ASCII, which is the American standard for yada, yada, yada. I always forget, all right? But it's ASCII. It's an 8-bit code, and I put part of it up here, all right? So every letter, every character gets 8 bits, 10111, whatever, okay? And you can decode those bits by finding the letter in the table and going up and taking a look at what the header is in the top, in the column, and what the row is, and it will tell you what ones and zeros go together to make the letter H. Now in this set, all of the it orders it from bit 7 to bit 1, where bit 8 is always 0. So we want H, we go up to the top, which is bit 7, 6, and 5, and we say, okay, 8 is 0, then I'm going to go 1, 0, 0. And I come over here, which is bit 4, 3, 2, and 1, and I go 1, 0, 0, 0. Boom, I have H. The keyboard understands it, the computer understands it, the satellite understands it. Okay? Now, everything has to have a code, including all punctuation and including spaces. Spaces have their own code, right? And again, you find the space in the chart, and you go up to bit 7, 6, and 5, and over to bit 4, 3, 2, and 1, and bit 8 is always 0. And you find that 0, 0, 1, 0, 0, 0, 0, 0, that will create a space. Computer knows it, you know it. Okay? Now, if you think about it, there are 12 letters, 12 characters, 8 bits apiece. It costs me 96 bits to send those 12 characters. All right, so 96 bits, that's not very much, but it's only one sentence, right? So if I have a whole letter to write, then it costs me that many more bits. Okay? Text is easy. What about pictures? Again, if you've used the computer and you've used any kind of draw program, then you have already used the color code that the computer uses. Okay? Everybody recognize this? All right? So this color code requires 3 letters for each color. A code for red, a code for green, and a code for blue. And they're all 8 bits. Okay? So that means I have potentially 256 times 256 times 256 possible colors. Let's see if I can find that. I did the math already because I knew I wouldn't remember it. Okay? So that means I have 16,777,216 colors. Well, maybe that's enough, right? I'm not sure I can distinguish one color from another that's off by one number, right? So I have that many colors. But the critical aspect here is that there's a finite number of colors that I can code. If there was an infinite number, I wouldn't be able to code it. Okay? So I take this picture and I have to cut it up into blocks. In other words, I pixelate it. And each block has a constant color. Now, the pixels on this image are really pretty big, right? Regular pictures have much tinier pixels. Right? But these are pretty big for just as an example. And so I point out that in that upper right corner, okay, if I wanted this color, in terms of red, green, blue, I would need red to be 0, 1, or 1, 0, 1, 0, 1, 0, 0, 1. And blue, I would need 1, 0, 1, 0, 1, 1, 1, 0. Okay? So that takes 24 bits for every pixel. Now let's think about that. How big is your regular iPhone picture? All right? So a standard, not a special iPhone, just a standard iPhone picture has about 4,000 pixels by 3,000 pixels. That makes 4,000 times 3,000 times 3 times 8. That's about 288 megabits, mega 10 to the 6th bits per image. That's why it takes up so much space on your computer. All right, so images take a lot of bits. But again, pictures are easy. Finite number of colors, pixels that are finite, right? So I grid it up spatially in a finite way, right? Code each bit, and I'm off and running, okay? But what about voice? All right, voice by its very nature is analog, not digital. It's not discrete in time, and it is not discrete in frequency. And that makes it difficult for me, because I have to make it discrete. I have to chunk it up. I have to make the pieces constant. Otherwise, I can't code them. Right? So how do I do this with this? By the way, that's actually my voice. This is my voice saying, "How are you?" This is the frequency content of that signal, of my voice saying, "How are you?" It takes 1.2 seconds for me to do that, to say, "How are you?" Okay? You'll notice on the frequency scale that voice occupies a band between 0 and about 20 kilohertz. Okay? So I can't talk much higher than that. You'll also notice that my voice tends to be lower than 20 kilohertz, because I have a lower voice than some females would have. All right? In order to recover what I am trying to say, if I were to sample the signal in the time domain, I have to sample it. In other words, I have to chunk it up into an adequate number of samples. For example, let's say I took 2 samples. I'm not really going to get my signal back on 2 samples. It's just not going to work. All right? So it turns out that there's a theorem called Nyquist criteria that says, there's some math for you, but basically it says that in order to recover the signal, I have to sample it at twice the rate of the largest frequency. So the largest frequency here is 20 kilohertz. So that means the rate at which I need to sample it is 40 kilohertz. Okay, you follow that? So I need to sample it at twice the rate of the highest frequency. Now it turns out that for audio signals, you typically sample it at 44.1 kilohertz. And the reason for that, we'll talk about a little bit more, the reason for that is to have a sort of a guard band, which I guess I'll point out in the next slide, all right? So what happens if you don't sample it? Or what happens when sampling happens? It's kind of magical, actually. So if I took a look at some sort of generic time domain signal, and it has some finite bandwidth, and then I'm going to sample it at whatever rate I'm supposed to sample in about. The act of sampling causes, in the frequency domain, for that frequency signal to duplicate. I haven't done anything to it, I just sampled it. You'd think I was losing information, but I'm actually not. I'm duplicating the spectral signal, and those duplications are separated by the sampling width, by the sampling time. Okay? I only want the middle one, but I get all these copies for free. Okay? But they cause me a problem. So if I don't sample at the right rate, then the copies will overlap. And that destroys some of my information. This is called aliasing. I only want the middle one, and I don't want it to be corrupted with all of the other copies, right? So if I don't sample it fast enough, the copies overlap, I have aliasing. I'll give you another example. There's a sinusoid. I want the dark one. That's the signal that I want, but I sampled it too slow. And you notice that based on the samples, I can't tell the difference between the black one, the dark one, and the dashed one. For all I know, I sent the dashed one. I can't tell the difference. So this is a form of aliasing, is that I haven't got enough samples to distinguish the frequency that I want. Okay? Now, I told you about the guard band, because in audio you actually sample faster than you need to. That's so that these copies separate themselves, so that when the rest of the electronics, or when the medium that I'm transmitting through spreads the signal, I still have a chance to get the pristine signal back without aliasing from its copy. Okay? So voice is a little bit trickier than the other ones because of this. Let's see. Oh, the other thing I forgot. So I chunked it in time, but that still gives me an infinite number of voltages or what have you, right, that I also have to quantize. Again, voice is quantized to 256 steps. That means 8 bits per step. Now you will notice that if I have a weak signal, those 8 bits, I might only swap a couple of bits. If I had a really strong signal, I might take the whole number of 256 steps. And that's kind of an awkward thing. And so typically what happens is we do non-uniform quantization, so that when I have a weak signal, I can have lots of bits change, and when I have a strong signal, I can have lots of bits change. But you don't really have to go there. It just has to say that I quantize. I not only chunk in time, I have to chunk in amplitude as well, so that I have a finite number of bits so that I can put a code to them. Because the goal is to have a code, all right? All right, so my 1.2 second, how are you, at 44.1 kilohertz gives me 74,970 samples. Each sample is 8 bits. So I have 599.760 kilobits for that 1.2 second. And I want to transmit that real time. Every single one of those bits. All right? That means that every single one of those bits has to be transmitted in about 2.8 microseconds. Micro 10 to the minus 6. That's how fast I have to be, just for those bits. It gets worse. But I have to be pretty fast. Okay? So that's coding. Now, once I've coded the data, and everything is ones and zeros, and we're all talking the same language, I need to transmit it. I want to make it go from here to there. Now my voice, mic'd up like it is, makes it really easy to go from here to the end of the room. But I'm not going over by the library. They can't hear me, right? And I'm certainly not going to North Pole. And I'm certainly not going to Virginia on my voice. It doesn't work, all right? So I can use radio waves, right? Radio waves propagate a fair amount, except for this problem called the ionosphere. All right, the ionosphere is a layer in the atmosphere of charged particles. All right? And the electromagnetic wave interacts with those charged particles, and if they are the right frequency, they get bounced back down towards Earth. And if they're a different frequency, they can punch their way through the ionosphere. So, anybody here ever driven across the Midwest from Chicago to Colorado? Anybody done that? Have you ever put your AM broadcast station on, and you can pick up a Chicago station all the way to Nebraska, especially at night, right? That's because AM radio operates in the kilohertz range, up to about a megahertz, and that cannot punch through the ionosphere. So AM radio, it goes up, it hits the ionosphere, and it goes right back down to Earth. And if you hit it right, you can listen to the Chicago station all the way to Nebraska, AM. FM radio occurs at a much higher frequency in the megahertz, and it can punch its way through. TV can punch its way through. It turns out that you have to be above about 30 megahertz in order to get to outer space. If you're below 30 megahertz, you're going to be bounced back down to Earth. If you're above 30 megahertz, you can move through the ionosphere up to the satellite. So we need to take our information, our ones and zeros, and we need to somehow get them on a signal that's higher than 30 megahertz in order to talk to the satellite at all, right? But there's worse things than that. you have the law. So lots of people want to use the airwaves. And again, if everybody's using the same frequency band, nobody can hear anything, right? So the Federal Communication Commission regulates who uses what. So you can see up there AM radio, very low frequency. You can see FM radio and TV. And by the time you get to satellite frequencies, you can't read the chart anymore because it's too small. But I tell you, the pink ones in here are satellite bands. That's where satellites can operate. So before you start building your own transmitter, you better make sure that you understand the laws, because FCC will come after you if you're in the wrong band, right? And probably the ham radio group will come after you too, right? All right, so we're going to obey the laws and we're going to get proper licensed and all of that kind of stuff. But we have to figure out, how do I get my information onto a frequency that I can transmit? That's called modulation. So here I have my information bits, 1010, and I have what I call my carrier, which is going to carry my information to the satellite. And that's at a frequency above 30 megahertz, all right? So some more math for you. That carrier is defined by an equation which has an amplitude, that's A, that says how big it is this way. It's a cosine, that just means it's a sinusoid. It has a frequency that tells you how many cycles I have in a particular second, and it has a phase that tells me how I'm shifting this back and forth, right to left, all right? Now, I can encode my information on the amplitude by changing the amplitude. I can encode it on the frequency by changing the frequency, and I can encode it on the phase. I can do any of those, all right? So if I do it on the amplitude, whoops, went backwards, sorry, I get amplitude shift keying, sometimes called on-off keying. Here, the amplitude is changed to reflect my information. So when I'm a 1, the signal's on. When I'm a 0, the signal's off. That's why it's called on-off keying, right? And there's an example of that. I can also do it with frequency. This is called frequency shift keying. So if I'm a 1, I have my carrier frequency, and what I'm doing is a differential away from it. So if I'm a 1, I might add a little bit of frequency, and so I'm a little higher than what my carrier is. And if I'm a 0, I'm going to be a little lower than what the carrier is. But you can still see the 0s and 1s in that signal. Finally, if I'm going to change the phase, what do you guess the name of it's going to be? Phase shift keying, right, yeah. Okay, so phase shift keying, I'm going to change the phase. When I'm a 1, I'm going to have the phase be 0. And when I'm 0, I'm going to have the phase be 180 degrees. Okay, and you can see here at the bit boundaries that I'm having a change of phase, an abrupt change of phase. Okay, so I have these 3 modulation schemes, and that's how I get my information on a carrier that has the right frequency that I can go into outer space, right? Which is essential, right? Because I want to talk to my kid. All right, so we can do more than that. Satellites, by the way, primarily use phase shift keying for a lot of reasons, which I'm not going to go into. But we can take a look at this in another way. So here's binary phase shift keying. That's the same signal as I showed you before, except I'm just showing you the phase, right? So there's a circle, phase starts at 0, goes around 180 degrees, comes back to 360 degrees, right? Phase shift keying. And if I do a 1, I'm in that pink dot that's at 0 degrees. And if I have a 0, I'm at that pink dot that's at 180 degrees. But if you think about it, I don't really have to stop there, right? I could have those dots. This is called QPSCoR, quadrature phase shift keying. And look at what I get. I have 4 symbols instead of 2, and that means I can send twice as many bits of information as I could when I was doing binary shift keying, all right? So each of those 4 bits, those 4 symbols now represent 2 bits. But wait, I don't have to stop there either. I can do 8 PSK. I can have 8 of them, right? And I could go on to 16 and 32, and it'd be great. I can do all this information with 1 symbol, but at a cost. So what happens really? What really happens is when I'm transmitting a signal, it picks up noise, because there's other things happening. That means that instead of being on that nice, pristine little dot, I'm somewhere in this bubble. The actual signal that I receive is somewhere in that bubble. Now, your eyes can tell, no problem. If I'm positive, I'm a 1. If I'm negative, I'm a 0. That noise doesn't bother me in the least, right? Well, let's put that bubble on the QPSK. Well, the bubbles are a little closer, but still no problem. I can make the distinction pretty easily. Your brain's pretty smart. It's a little harder for electronics to do it, but your brain is pretty smart, and you can tell which symbol I'm trying to send. Okay? Let's put the noise on the 8 PSK. Ooh is right. Good comment. Ooh is right. So now I have overlap. That means I can't always tell what symbol I was sending, right? So there's a limit in terms of what kind of modulation scheme I can use for a particular noise environment. And in fact, there's an equation for this. I knew you'd ask. This is called the Shannon limit, okay? The Shannon theorem says that the capacity of the channel, so the channel is the space between the transmitter and the receiver, all right? It's whatever happens to be in there, whether it's air or ionosphere or outer space. It's whatever that channel is. The capacity of the channel is a function of the bandwidth, right? So if I have more bandwidth, I can put more data down. If I have small bandwidth, I can't. And the signal-to-noise ratio. So if the signal-to-noise ratio is too big, or too small, rather, meaning that there's more noise than signal, then I better be transmitting BPSK, because I can't figure out what the symbol is, okay? If it's a large signal-to-noise ratio, meaning those bubbles are small, then shoot, I can do 8 PSK and get lots of information down, okay? So we've encoded, we've modulated, okay, so that we can transmit. Let's talk about, let me see, what else? There were lots of people who wanted to talk all at the same time, right? How the heck am I going to deal with all of those, right? This is called multiple access. And again, things come in threes, all good things come in threes. We have 3 different solutions to providing multiple access. We have frequency domain multiple access. This is where I take my bandwidth and I chop it up into different frequency subchannels, and I say, you get this subchannel, you get this subchannel, and you get this subchannel over here, and you will not talk on each other's subchannels, okay? And if you do that, then nobody interferes with each other, right? You're on different frequencies. I can do time domain multiple access. That's when I chunk up time, and I say, all right, here is my bit time, and the first subsection of it you get to have, and you're always going to transmit all of your pieces in that first, and then you're going to be quiet every other time. That's sort of like having a conversation. I get to talk, then you get to talk, then you get to talk, okay? The last one is code domain multiple access. This is where I give you a code that's your special code, and magic happens, and even though everybody else is talking at the same time, if I want to hear your conversation, I just plug in your code and everybody else goes silent and I get to hear you. And it really is like magic, you know. So let's take a look at each of these and see what they look like. All right, so this is frequency division multiple access. I have 3 different frequencies. I'm doing amplitude modulation, meaning I am changing the amplitude of the carrier signal. So there's my information, is the baseband signal. I have my carrier, 3 different frequencies. I get my bandpass signal, which is I've already modulated my information onto the carrier, and I just sum them up. And then I have that garbage clear off on the right. And you're like, well, what the heck? How am I going to get my signal back? Right? Because you want to get it back. Well, I take my signal, and I put it through 3 different filters. The filter selectively looks at only your frequency. Okay? So I have tiny little filters, and they say, okay, your frequency 1, here's your filter for frequency 1. Your frequency 2, there's your filter for frequency 2. It will let pass your frequency, and it will kill everybody else's frequency. So it doesn't matter that I added them all up, right? So once I get your specific frequency back, I remove the carrier, and I get left with the information. Easy peasy, right? What about time domain? Time domain, again, you're just chunking up time. You have 2 people who want to use the channel. I have 2 time slots for them. The first one wants to say hi, and the second one wants to say go. And so there's the G's in time slot 1, then the H, and then I'm going to do the O. And then when it gets to the other side, I just divide them back up, and I take everybody in time slot 1, and I go boom, 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 concatenate it all together, and there's your go or hi or whichever one it was. All right? So again, not too difficult. And actually, time domain works pretty good because most of the time, actually, we don't say anything. Right? When we're talking about microseconds, most of the time we're not saying anything, so it's pretty easy to chunk it up. The difficulty with time domain, if you're going long distance, is that the 2 signals may not stay synchronized, okay, if the distance is different. And then they can overlap and interfere with each other. Okay, so that's a problem. Now the magic happens with the codes. So you got to do math here for me. So the other one, code division, multiple access. So I have 4 users, and each user gets their own code. There you go. For every bit that I want to send, in this example, I'm actually going to send 4 bits. I'm going to send the 4 bits of the code, all right, for every bit. So those 2,288 megabits for that picture that I wanted to send, now multiply that by 4, okay? Before we get into the math and the magic, I want you to pay attention to the fact that CDMA, actually the code length that you use, which is used in your cell phones all the time, tends to be on the order of 215 to 256 bits long. So every bit you want to send is now multiplied by 256 bits, okay? And eventually you want this to be real time, right? You want to stream your movies real time, you know. That means I have to send those bits that much faster. All right, so how does this work? What I do is I take my data, I multiply it by the code, everybody does that, I add them all up, and I transmitted the sum. So let's do this. User 1 is going to send a -1. I'm going to multiply his code by a -1, and I get -1, -1, -1, -1. User 4 down here wants to send a +1. I multiply +1 by his code, and I get +1, -1, -1, +1. User 3 is silent, it's sending a 0. Multiply it by his code, and I get zeros. And I'm going to take bit 1 in all of them, add them up, I get -1. Bit 2 in all of them, add them up, I get -1. Bit 3 in all of them, add them up, I get -3. And finally, bit 4 in all of them, I get +1. And you're looking at that and you're going, how the heck am I ever going to know what these guys sent? Right? Who is not thinking of that, you know? It's like, how the heck do I know how these guys sent? Well, it's magic. I'm going to get the code, I'm going to get the signal, I'm going to multiply it by the code, I'm going to add up the bits, and I'm going to get my number back. Believe me? Here we go. There's the thing that was sent, -1, -1, -3, 1. Here's his code, +1, +1, +1, +1. I bitwise multiply those together, -1, -1, -3, -1. I sum them all up, -4, divide by the number of bits, which is 4, boom, I get -1, which is what he sent. Pretty slick, huh? Let's try this one. -1, -1, -3, +1, multiplied by this guy's code, +1, -1, -1, +1. Multiply them together bitwise, add up all the bits. I get 4 divided by the number of bits, 4, +1. That one up there is the same -1. Let's check this 0. Surely I can't get 0. Well, here I go. Here's the signal, -1, -1, -3, and 1, multiplied by the code, +1, +1, -1, -1. Multiply them together, add them all up, equals 0. Pretty special, huh? So, code division multiple access sometimes is called spread spectrum. If I have a unique code, and the codes have to be special. I haven't gone into why they have to be orthogonal and all that other kind of stuff, but they're special codes. They can't be just any old code. They're special codes which allow me to encode my data, mix it in with everybody else's data, and still get my data back again. It's pretty special. All right. So, how to talk to satellites? Take my information that I want to send. I encode it so that I can translate from my language to the ones and zeros that the satellite understand. I modulate it onto a frequency that will transmit through the channel that I need to transmit through. If I need multiple access, I allow for other users to use the same space, because we all like to play nice with each other, right? I give it power to get up to my geosynchronous satellite, which is 36,000 kilometers away, which pretty much is the circumference of the Earth, just FYI, that far away. It receives it. It's a really weak signal by then, so it pumps in more power, translates it to another frequency, and I do the exact and backwards to receive it. I receive it, I separate it into its various channels, I demodulate it, I decode it, and I get my picture back. Right? And that's how you talk to satellites. Now, I have a few more minutes before I go to questions. What are we doing at the university concerning this stuff? Well, I'm telling you, up at the Geophysical Institute, there's a lot of really smart researchers who are taking data from outer space, right? Either in situ data about the aurora, or magnetic fields, or high-energy particles, or whatever have you, right? And they take that data on satellites, and they need to get it down to the Earth. And if anybody was here for the NASA guy, the first talk, Alex, I forget what his last name is, and he had all of that didn't he have great movies? He had great movies of the sun burbling and boiling and spewing off stuff, right? And all the satellites that collect that data, they need to get that data down to Earth, right? That's a lot of data. So what we do in my lab is we have an Air Force project to design a communications satellite that will allow us to explore and experiment on different modulation and coding schemes to try to maximize the amount of information that comes down to Earth. So let me show you a little bit about how that works. So a traditional satellite, if it's not geostationary, then it moves overhead, right? Which means I have to track it. And there's things on the satellite that allow the antenna to track the ground station. Okay, so that's pretty standard. If you have a scientific instrument that needs to always look at the ground, or needs to always look at the sun, or needs to always look at anything, you don't want your satellite to slew, right? Because it will lose what it's looking at. So what you'd like to have is you'd like to have the antenna slew and not the satellite. So our satellite has an experimental payload called a phased array, which allows the antenna to point without pointing the satellite. Okay, that's number one experimental payload. The other thing we want to do is we want to take advantage of the fact that the signal-to-noise ratio changes as the satellite moves overhead. It becomes, when it's out on the horizon, it's far away, it has less signal. When it's directly overhead, it's closer, the signal is higher, and then it becomes lower again. In a traditional pass, you have a standard modulation coding speed, right? And you get enough data, you know, when the signal-to-noise ratio meets that, so BPSK. When I get enough signal that I can meet my channel limit, then I get information through. But I've wasted a lot of signal-to-noise ratio, right? And so the other payload that we have is a software-defined radio, and what it's attempting to do is match its modulation and coding scheme with the signal-to-noise ratio as it goes overhead, with the attempt then to improve the amount of information that you get down. Okay, so that's what we're doing up. This, by the way, this was a proposal that a graduate student and I wrote a year or so ago to the Air Force. They funded it. He's now working at Goddard, working in satellite communication, which is pretty cool. Okay, so last thing to tell you is that the SSEP lab takes on visitors. You're welcome to come by. You're welcome to take a look at our satellite.